Hello. In this short presentation, I will explain and solve a standard physics problem rooted in Faraday's law of induction. This problem reveals the fundamental physics behind the electromagnetic braking systems used in trains.
Amazing!
Before we begin, let me remind you what an electromagnet is. An electromagnet is created by passing an electric current through a coil of wire, typically wound around a ferromagnetic core. The strength of the magnetic field depends on the current applied. This picture is an example of a linear eddy current braking system on a locomotive.
Trains use large electromagnets that are deployed near the tracks and energized with current when braking is needed. This system activates when the operator applies the brakes, generating resistive forces to slow the train down.
And now let's look at an example problem related to Faraday's law of induction. Although this problem won't explain the engineering design of magnetic braking systems, it will explain the fundamental physics behind how they work. A rectangular loop of length L, mass m, and resistance R is launched with an initial velocity, v0, into a uniform magnetic field B. Assume the loop moves to the right along the x-axis and enters the field at t equals 0 seconds. A. Derive an expression for the loop's velocity v as a function of time t after it enters the magnetic field. You can ignore gravity. These are the given constants. v0 is 10 meters per second. The length of the loop is 0.1 meter. The mass of the loop is 1 gram or 0.001 kilogram. The resistance is 0.001 ohms. And the magnetic field is 0.1 Tesla. Let's look at the solution to this problem. Faraday's law tells us that if flux changes over time, an EMF will be produced, which will drive current in the circuit. Flux is equal to B times A. For this problem, the area of the loop that's in the magnetic field is equal to L, the length of the loop, multiplied by X, where X is the width of the loop that's in the magnetic field. X is the distance from this dotted line to the edge of the loop. Flux is equal to B times A, and that's B times L times X. EMF is negative the time derivative of flux. B is a constant, L is a constant, X changes with time, X is this distance, and the loop is moving to the right, so X is changing with time. The EMF is equal to negative BL dx dt. dx dt is velocity, therefore the magnitude of the EMF is BLV. If we have the EMF, we can calculate current using Ohm's law. Ohm's law tells us V equals IR, or I equals E over R. This gives us an expression for the current in the loop. The current is flowing counterclockwise because of Lenz's law. When a current flows in a magnetic field, the Lorentz force tells us that there's going to be a force on that current. To get the force on the current flowing upward, you take your fingers and you point them in the direction of the current and then you curl them into the magnetic field. You'll find there's a force pushing the loop to the left. The force is IL cross B. This is a 90-degree angle, so we don't need to worry about the cross product. Therefore, the force is equal to I times B times L. We just calculated I, it's BLV over R. And therefore, the force acting on this loop is equal to B squared L squared over R times the velocity of the loop. Newton's second law tells us that force is equal to mass times acceleration. This is the force formula that we just found on the previous page. The negative sign comes from the fact that the force is going in the opposite direction of the velocity. M dv dt is equal to this formula, and this leads to this differential equation. This is a differential equation that allows us to solve for the velocity as a function of time. This is an easy differential equation to solve. I solved it the hard way here, but ultimately what we find is that the velocity decreases with time. The velocity is a negative exponential. The velocity starts out at some value, 10 meters per second, and it gets slower over time, and it's slowing down because of the Lorentz force, which comes about because of Faraday's law. This is the explanation of the fundamental physics behind magnetic braking in locomotives and trains.